That is 1/3 of 100%. On the last call, my radio I've now set it off. Is that all? Fair.
Also, if you have a device that accesses the internet, please log on to Blackboard, our section 001 for lecture, and click the link to Echo 360 from there and let me know whether that works. If you've already done that and set up a cell phone number in your account, then you can text message an answer, but I'll show that when we get to it. If you want to get a copy of slides.
Thanks. Yeah.
You want to get your pre-test and a copy of slides for today. Get your pre-test and a copy of slides for today. Get your pre-test in alphabetical order and a copy of slides for today.
Mine is not here.
Someone may have grabbed it for you, or let me check that I had one recorded for you.
What's that here either?
Check it out.
Hey,
Yes.
I definitely turned mine in, and I'm gonna have it up here.
Put it in the box. Okay, so I have. Well, now let me make sure if I have a grade recorded for you that you turned it in.
Yeah, I just put it in the box outside your office.
What's your last name?
Hallie?
I do not have one for you. If you can, there's a copy of one online. If you can print out another one for me, I won't count it later or whatever, but I didn't have one recorded in that.
Okay, that's weird, but yeah, I'll do it again.
Just give it to me next week.
Cool, thanks.
Jury?
Yeah.
I don't have one for you there. So something you can print out online and turn it into the I did, but I printed out 4 copies and I haven't. They are slides and things.
Okay, no problem.
Oh, hey, do you have extra copies? Okay, we'll go ahead and get started. So today I have things by slides. I probably will not be always doing things things by slides, but I want to go quickly enough of what should be a review for most of you based on the pre-test, but particularly if you've got a very low score, less than about 40% on it, then you need to make sure that you're comfortable with these topics that we're going to talk about today. If you got a higher score, these may be completely a review for you, and that's fine, but I want to get everyone up to the same pace from it. So, we are in an electric circuits class. First of all, what is an electric circuit? An electric circuit is simply an interconnection of electric circuit elements. Although it's kind of annoying because you're using part of the definition, part of the word in the definition from it. So what's an electric circuit element? Electric circuit elements could be lots of things. Basically any sort of electrical component. Most common ones we'll talk about are resistors. So I expect you to be familiar with resistors, and we'll talk more about them today. Voltage sources and current sources. Those are the three that I expect you all to be pretty familiar with and comfortable with using in circuits and calculating things for. Other circuit elements that we will talk about later are capacitors and inductors. I know you cover capacitors somewhat in physics, although from most people's pre-test ability to calculate things on capacitors was not great. So I'm kind of going to assume that that was not something you were very strong in at this point. Inductors, a lot of people said that they didn't do anything of calculating with inductors, so we may or may not get to that. Op amps we will also cover in this class. I know no one seemed to have familiarity with those, although some people were able to look up enough online how to do a simple thing with op amp, whether you knew what it was doing or not. The other two circuit elements that you'll cover in later courses, but not in this course, are diodes and transistors. These are semiconductor elements, so they behave a lot differently than our traditional elements like resistors, voltage sources, and capacitors and inductors. You will get to them in sensing and measurement, which is the course after this one that builds on it. So this knowledge is going to build through for a while, and you will cover those elements in that class. Okay. So, current is one of our basic electrical properties. Current is just defined as the time, rate, and change of charge. It has the symbol I. Does anyone know why in an equation we use the symbol I for current? It seems rather stupid, because there's no I in current, right? Not the way I spell it, at least. From it. So C was already used for capacitance, and then sometimes charge. And the French were who discovered current in the actual as a measurable property. And they called it intensity of current from it, although in a French accent or whatever the French words from that were. And so it got labeled with an I. So don't be confused, but anywhere you see in an equation an I, that is current. Since it is the time rate of change, that I, as a symbol in equation, is defined to be, and this symbol here means is defined to be, so it kind of looks like a triangle with an equal sign. The derivative, so D, of charge, which is written as a Q, dt. So if I were to have a graph of charge in time, of how many charges were moving in time from it, and I took the derivative of that graph, I would now get current. So it's talking about charges moving in time. It has the units of amps, or amperes, that get the symbol A. So you could have 1.5 amps, things like that. And by medical things, we're talking about normally very, very small currents. So we'll normally be more in something like milliamps, microamps, or even picoamps. So if you're getting lots of amps, probably even actual 1 amp or more range from it, it's probably not right for what we're doing. Electrical engineers may be dealing with that amount of current. When you're talking about current supplied in a power supply system, we're normally talking about very small amounts of current moving in time. Your body is not generating large amounts of current. So when we measure things in the body, that's normally a very small amount from it. There are two types of current, AC and DC from it, like the band if you're a fan of AC/DC. AC stands for alternating current from it. It is just current that changes in time. It can change however it wants to in time, but as long as it is not constant in time, it is part of AC circuits. So this could commonly look like a sinusoid wave. From what it looked like on the pretest, no one seemed to be very comfortable when you were given a sinusoid equation into how to then calculate that in the circuit. We will get to that later in the semester of how to calculate truly AC circuits from that. So it could look like a sine or cosine. That's the most common for what's supplied in wall power outlets. So in the US, It's actually a voltage supply, not current. We'll talk about the difference between that. But it is oscillating. It is not staying constant in time, and it oscillates at a rate of 60 hertz, which is 60 cycles per second. Okay? That's just what's used to easily transfer electrical circuit energy through big wires. So it's applied power to your house, so you can plug in your laptop or your TV or whatever. That frequency is kind of arbitrary. It's what's used throughout the U.S., where all power stations are making 60 hertz worth of oscillations, but in different countries or different places, that rate can be different. So in Europe, they use 50 hertz. No real reason they chose 50 over 60. When you get into sensing and measurement, particularly later, and when we talk more about AC circuits at the end of the semester, you realize that 60 hertz causes a big problem for a lot of things we want to measure medically, because there are a lot of things that we have that overlap with that frequency, which makes it really hard to tell what we want to measure from that wall power. But do note that anything you have plugged into a wall is oscillating in time, and in the U.S. that's oscillating at 60 hertz. If you were on a Navy ship, they oscillate at a different frequency, so at about 360 hertz then. Again, the reasons for that are different from it. DC is what's a lot easier to calculate and what we will start working with in this class, and what you probably should be more familiar with. It stands for direct current. Really just means current that is not changing in time. So if this was my graph of time was my x-axis and current was my y-axis, and it could look like a sine wave for AC, what would it look like for DC if you graph time on an x-axis and current on your y-axis? Yeah. It'd be a straight line. Yeah, so it's going to be a straight horizontal line. That horizontal line can be wherever you want. You know, if you had 1 amp of current, it might be at 1 amp. It could be at 0 amps and not have anything going through it. That's still DC. It could be up at 10 amps or wherever. It just needs to be perfectly horizontal. There can be no change in time. AC, besides looking like sine waves, which is the most common, could look like anything else changing in time. So I could have square waves, where I'm switching current off and on, or changing the direction or polarity of that current. I could have things that don't even look like any mathematical equation that we're used to. So something like this, which is actually more voltage, and if I were good at graphing it, could be something like an EKG. So if you're trying to measure electrical current, or in that case voltage from the body, from it, it could look like a variety of shapes from it. So this is from our P wave, is from our atria depolarizing, and then we get QRS from our ventricles depolarizing, things like that. Most of the time we talk about AC though as it is repeating. That does help us analyze those signals a little better, versus if it were just a single change in time. But both of them would really be AC versions of it. It's just a lot easier if that's a repeating signal, whether that's a repeating square wave, or a repeating EKG graph, or a repeating sine wave. We will start though with DC. It's a lot easier to calculate things in DC, but we will be moving on to AC in the second half of the semester, because that's really where things get interesting. If current and voltage are all the same in time, then that gets pretty boring. It doesn't tend to be a lot of what we actually want to measure medically. Current, if you have a current source, should look something like this. So it should be a circle with an arrow through it. That arrow is telling you the direction of current, because current is a vector. And if we remember from physics, vectors mean they have to have both a magnitude, tells you how large they are, and a direction. Any Despicable Me fans here? Anyone like the movie Despicable Me? What's the evil villain in Despicable Me? Vector. And why is he called Vector? Yeah, he's committing crimes with both direction and magnitude, right? So it's like our great example of teaching little kids about vectors from it. So when you think about current, if you were giving me an answer for current, and you're like, oh yeah, it's just 1 amp, make sure in your head you're asking yourself, that's 1 amp in what direction? Because 1 amp in one direction, if I go this way, really equals negative 1 amp going the opposite direction, okay? So you have to know what direction that current is going through. Voltage is our other electric circuit property that you should be familiar with. Voltage is defined to be the energy required to move a unit element of charge. So it's our nice symbol Q. Normally we talk about those unit elements in coulombs. right? But like an electron moving through something, through a circuit element. So if I move it through a resistor or through a capacitor or whatever element. The easiest way to think of voltage is potential energy, particularly because people often get confused as to whether they're defining voltage or current for a system. But if you think about potential energy, that tends to make it a little easier. So in physics, potential energy tells you that if you're standing at the top of the hill, do you have more or less potential energy than if you're at the bottom of the hill? Top of the hill compared to the bottom of the hill, which one has more potential energy? Top of the hill, right? Because even without you expending any energy, if you fall, you will roll down the hill due to gravity from it. Voltage is the same idea, that if I have something at a higher voltage compared to a lower voltage, current will naturally flow from higher to lower, just like water downhill, just like you downhill from it, with gravity from it. It does not take any energy to do that. If I want to go the reverse direction, though, from the bottom of the hill to the top of the hill, then that takes work, right? And I've got to expend some energy to get up that hill. The same thing relates in electric circuits. So if I have something like a voltage source that looks like this, they're normally labeled with a plus and a minus. The plus side is telling you what side is higher potential energy or higher voltage than the minus side. So all this means is that this side of my source here, this is a voltage source, is 5 volts higher than this. Okay? If I define this to be 0 volts, then this one's 5 volts. The problem is that we can't ever define any absolute voltage. Just like you actually can't define absolute potential energy either. What do we compare potential energy to? Where do we say you have like 0 potential energy on the Earth? Yeah, like at sea level, right? But that's kind of arbitrary. You could define potential energy compared to the bottom of the Marianas Trench, which is the deepest part of the ocean from it. In which case, sea level is way above that, right? So it's all relative, and you have to know where you're comparing to. Does anyone know what we compare our voltage potential energy to in circuits? What do we call that comparison point? Because it's not sea level. Yeah? Ground, yeah. So it kind of, again, is acting like potential energy, except we'd make this arbitrary thing that we call ground. Now, on Earth, we know ground can be a lot of different levels, right? But in electric circuits, we define this arbitrary place on a circuit to be ground. Now, normally, it's called ground because if you actually have the ground prong and a wall outlet, it is attached to a giant metal pole that is physically going into the ground of the Earth. And we assume that you can put as much charges or as much current as you want into that pole, and it will not change the overall charge built up of the Earth, right? Just like you can pour as many tiny cups of water into the ocean, and we assume it's not going to raise sea level. We just assume that Earth's ground can hold an infinite number of charges. And that's normally a pretty good assumption, and is what literally is going on to make the safety of your house, is that you can put charge or current into the Earth and assume it's not going to change anything from it. And we measure everything relative to that. So we tend to call ground, the symbols for ground, you may be used to a line or 3 lines, one longer and then 2 shorter from it. Ground can also look like a triangle. Both of those mean the same thing, but we compare it to this. So if I say this side is 5 volts, that means I'm comparing this side as being ground. Voltage sources can also look like, they can have an AC or DC as well. If it is just this plus and minus sign in a circle, this is a DC voltage source. If there is this little sine wave in the middle, it looks like a squiggle, that is representing an AC voltage source. Just letting you know it is changing in time. Again, the most common way of doing that either is a sine or a cosine equation, and we will get to those later. But this still means a voltage source, this side being more positive in voltage than this side, or like higher up the hill. Another way to draw voltage sources, just to make it more confusing, is that there are different symbols for it, depending on where you look, can be one long line with one short line. Do not confuse this voltage source with ground. Okay? Ground has 3 lines. That voltage source has 2. If you mix them up, you're not going to know what that is. Normally, They always should have a plus, and it might say something like plus 5 volts or something from it. It's a hint to you. Ground will not have any label next to it. So there is a difference between those two. Again, the easiest way to think about is like potential energy. So if here's my little stick person at the top of the hill, compared to the bottom of the hill, he has higher potential energy than the guy at the bottom of the hill from it. Same thing that if I have my voltage source, the person up here has higher voltage or higher potential energy than the person down here. That's all that means. But I've always got to compare it to some point. For easy reference, we compare it to what's called the electrical ground from it. I only get a gain in voltage, as in go from the bottom of the hill to the top of the hill, when I have something that is supplying energy to my circuit. So that's normally a battery, or wall power, or a generator, something that is giving energy into the system. So that's why you need a battery to run a toy, or it's why you need the battery in your laptop system from it. It's got to supply energy to it. Everything else is losing energy. Their energy sucks. So resistors are using up energy. You can think of that as like the screen on your computer is using energy. The longer you keep that computer screen on, the less energy you have stored in your battery left from it. Most things are going to act kind of like resistors. Other things we'll talk about circuit elements later, capacitors and inductors, and things like that, do tend to also use up energy, but in kind of different ways. A resistor is the most simple thing that uses up energy. So in a battery or wall power, we define current, so if this is my 5 volt voltage source, we define current to actually be going from less voltage to higher voltage. We are gaining voltage or energy through a battery. But through a resistor, I should be losing energy. Resistors are never going to supply energy to a system. So I should be going from a higher voltage to a lower voltage from it. Okay? So again, with current being identified by the direction of an arrow, if I label these arrows as my current I should always have current going this way through a voltage source and this way through a resistor in general. Now, some of the time, voltage sources, if you combine them in weird ways, if they have another voltage source or current source with them, can be going in reverse directions from it, but a resistor will always be losing energy in the direction of current going from it. So it will lose voltage. What is a resistor? A resistor is simply something that resists the flow of electric current. Its symbol is R, and its unit is ohms. So every time you think of ohms, you can do like a little yoga chant. Be very calm and relaxed from it. It's what I think of as ohms. The symbol for that is the Greek letter omega from it. Resistance is defined by the equation R for resistance equals rho, where rho is your resistivity of a material. So if I change the material, I can change its resistance. L is the length of the material, so how long I go through it if I think about it like a cylinder here. A is the cross-sectional area of that material, so rho L over A. So with rho being the resistivity of a material, if resistance is simply the ability of something to resist the flow of current or try to prevent electrical current from moving through it. Can anyone tell me a material, an element or something we use in everyday life or encounter in everyday life that you think would be a good resistor, as in it would not allow electrical current to flow through it well? There are lots of things. So. Rubber is generally a good one. That's why we tend to insulate all of our wires and things with something that kind of resembles rubber or plastic things. If not, when I grab this wire and if there's current going through it, then I would be shocked, right? But if that rubber is not good at allowing current to go through it, it is a good resistor, then I don't get current going from the wire into my body, which is a good thing most days. What's preventing current from just jumping out of a wall outlet onto my body? What's in between me and the wall outlet? Air. Is air a good resistor? Yes, for the most part, and we certainly hope so. Otherwise, again, you just have sparks flying like crazy. So what are good resistors? Things like air, rubber, a lot of plastic materials from it. What we actually tend to make resistors out of, and what we'll be using as our resistors in lab, are carbon film. And carbon in general is not great of an electrical conductor because it has 4 valence electrons that it likes to share equally, and so it's kind of all set with where it wants its electrons to be. It really doesn't want them to move well from that, but it depends on how you design those materials from that. What would be a bad resistor? And think of a material that would not be a good resistor. Sorry, what was it? Copper, okay. So copper is what type of element? It's a metal, yeah. So we think of most metals as being very not good resistors. What do we call them instead? They're good conductors, yeah. So the opposite of resistance is conductance. So copper, there are a lot of other metals. You could be titanium. We tend to use that a lot for wires or things inside the body because it doesn't react with a lot of things inside the body. Even the men of our body is naturally metal, so it's kind of a hard thing when we try to put electric circuits in the body sometimes. Anything else that would be a bad resistor? Why do they warn you not to go swimming in a lightning storm? What's conductive? Yeah, so water, particularly with electrolytes, so swimming in the ocean would be worse than even your pool, but your pool probably has some ions in it. And even normal water will dissociate normally into some ions. Particularly, what I'm going to call ionized water, is a good conductor. That's a problem because what is most of our bodies made of? Water, which means if you didn't have that rubber insulation on that wire, it would be pretty likely to want to flow current from the wire into my body from it. Now your skin is pretty electrically resistive, and that helps you somewhat, but not extensively. That's what happens when people get electrocuted or shocked from it, is that you're getting current into your body. Because all that water in your body is a very good electrical conductor, and that can be a problem if you're not wanting to send electrical current through it. That's great when you do want to, and your cells, when we want our heart muscles to send electrical current to make our heart beat or our muscles contract, then that's great that we have water. If you don't want current though, that's a problem. We assume since most metals, copper, titanium, even things like aluminum, gold, silver, almost any other metal you can think of, are pretty bad resistors and therefore good conductors from it. We assume that if we use wires that are made of metal, that they have pretty low resistance. They're not good resistors, they're bad resistors, which means low resistance from it. We assume that's a resistance of 0, although that may be a bad assumption from it. So what happens when you choose a longer wire versus, or you use more wires in a circuit from it? So anything of that wire can be thought of like this cylinder here. What happens is I increase that length L. That's going to be our first Echo 360 question if you have your device handy. Oops, except I went back on it. There we go. So how does resistance change as the length of a wire increases? Does it A, does the length of the wire not affect the resistance? B, the resistance decreases? Or C, the resistance increases? If you're logged on through it, it should be a little presentation next to today's date that you can then select an answer. If you're texting, you have to text to that number. It's not working on this.
I sent my email, and then it has one. What email are you using? And you got this on the blackboard.
see what I can get of information of troubleshooting from it. I'm not collecting today's for a grade, we're just practicing it from it. But, okay, for people who have been able to get through the system, have you submitted an answer or need more time? Okay, survey says this, yes. So our resistance should increase. So even though we like to assume that wires have no resistance or very low resistance, it's really that they just have low resistance. But the longer you make them, the more resistance that's going to be. So when you're building a circuit in lab and you choose the longest wire possible, you are adding more resistance to your system than you think you are, okay? So don't do that. Similarly, if you have 5 wires to go to someplace versus just using 1 wire, don't do that either. It's better to use less wires or shorter wires because it will make your system have less extra resistance than what you thought from it. So anything, the longer I need to go, the more resistance it is. I tend to think about resistance kind of like traffic. If you talk about cars driving on a street, then the longer I have to go down that road, the more time it's going to take me from it. And if there's traffic acting like my resistor, then that's increasing my effort to get from point A to point B. It's the same thing with the little charges in the circuit. To get from point A to point B here, they've got to go through this whole length. The longer that is, the more resistance that becomes. If I increase my cross-sectional area, if I increase A here, what happens to resistance? It decreases, has a reverse effect. This is like adding more lanes on your street, right? If you're on a 6-lane highway versus a 1-lane road, then you can get more traffic through to the same place in time. So if I make my resistor wider so that they're more like lanes for my charges to move through it, then that's easier from it. We talked about the material. Choosing a different material that has a higher or lower resistivity will also change that. We will assume in this class anywhere that is just assumed to be wires has a resistance of 0. But keep in mind that, again, it's a bad assumption. The longer you make those wires, or the thinner you make those wires from that as well. Okay, we're now going to get to probably the only equation anyone ever remembers from electric circuits, which is Ohm's law. And I do assume that you at least have heard of it from physics and vaguely know how to use it. So Ohm's law says that voltage equals current, remember this I is current, times resistance. I will always try to write Ohm's law as delta V, as in a change in voltage. Because remember we said we can't define an absolute voltage anywhere? Voltage is an energy difference from one point to another, just like potential energy. So there's no like absolute voltage where I get up to, this is actually 100 volts or something. It's 100 volts compared to ground. So it's a change in voltage from one point to another. And you've got to realize that this is always referring to a change. It's not telling you an absolute voltage at a point. Okay, so this delta here means a change in voltage. I expect you to be very familiar with this equation, be able to solve for it forwards, backwards, sideways, and upside down from it, which means that you should be able to plug in a current and a resistance and get out voltage. All I have to do is multiply current by resistance to get voltage. But I also expect you to be comfortable with solving for current instead, which current is solved for as the change in voltage over an element over the resistance. So if it's a resistor, that's really the only thing Ohm's law applies to. It is the voltage drop over that resistor. Remember we said resistors will always lose energy over its resistance. I could conversely solve for resistance. If I knew the drop in voltage over that resistor and the current that went through it, then that resistance equals the change in voltage over the current from it. Again, this is referring to a voltage drop, never an absolute voltage, and it tells me that this voltage drop is proportional to the current flowing through a resistor. If I increase the current, I increase the voltage drop from it. Conversely, if I increase the voltage drop across something, I'd increase the current if it is the same resistor. So this would normally be drawn that if I have a resistor here, and this side is positive 5 volts compared to if this is my ground, which we think of like 0 volts, again there's no absolute from it, then current will always be going from positive to negative. It will always have a voltage drop across it. So I expect you to be able to identify that if there is a direction of current arrow, it's going from positive where it starts to negative where that arrow ends. My arrow is going like this, and then my positive was down here, and my negative was up here. Because I can't gain voltage going through a resistor, all I can do is lose it. It's like spending money in a store. You can't come out of the store with more money than what you went in. Keep in mind that Ohm's law only applies to resistors. It's going to be really tempting, and a lot of people wanted to be tempted on a pretest, so even when you get something like capacitance or inductance or something that doesn't look like a resistor, you want to use Ohm's law, and you want to use it really badly because you're comfortable with it, and it's the only equation we remember, right? But it only applies when I have a resistor. If it is not a resistor, then I can't just decide, oh yeah, a capacitor I could plug in there. It does not work the same way. Now, with that caveat, we will learn a trick at the end of the semester that we can write capacitors or inductors, or two other circuit elements that we'll talk about, like resistance. But it involves some fancy math. It involves imaginary numbers, and it involves keeping up with things from it that are a lot more complicated than just plugging in the capacitance value from it. So otherwise, they do not behave at all like resistors. If they behaved like resistors, we call them a resistor and not a capacitor, right? So they had different names for a reason. Ohm's law only works with our resistors. Any wire we assume has a resistance of 0. Again, we assume it's a bad resistor. It's a good conductor. So what is the voltage drop over any wire? If the resistance is 0, what does that mean delta V is? 0. Does it matter what current that is? No. So in theory, I can put 500 amps of current through a wire, and I assume I did not lose voltage anywhere through it. So this means that even if I have resistors, oh, and I should have drawn my symbol here. A resistor, I assume, looks like this. It kind of looks like sharp squiggles. I don't have a better way to describe the sharp squiggles, but that. Okay. Here's a resistor, here's R1, here's resistor 2. In between them, if I'm just drawing a line, I'm assuming that is wire. So although I can have a voltage drop, which I'm going to call delta V over R1, and a voltage drop over R2, did I lose any voltage in that wire there going between them? No. And it doesn't matter which direction I draw it or how long I draw it, in theory. Okay? So we're going to assume that although you had a voltage drop here, if this went from, let's say, 3 volts to 2 volts, which meant it had a voltage drop of what? 1 volt. Then I'd still be at the same 2 volts here. Anywhere is connected by wire is held to the same voltage. So anywhere connected just by wire and I'm angular is held to the same voltage. Okay, so you're going to assume there's no change in voltage just through a wire. When we were building circuits this week, this means practically that anywhere that just had wire, you can connect to the same point. It's really telling you this is the same place. Again, voltage being like potential energy, this is telling me that it has the same potential energy as anywhere else from it. So I can assume that's like the same place geographically. And anywhere else may be above or below that if it goes through an element. Okay. The other thing I expect should be somewhat reviewed for you is defining what is in series. What does it mean to be in series? Elements are said to be in series if there are no other choices for a path for current to flow. Okay, so circuits I'm going to refer to as being kind of like little mazes. If you like mazes or puzzles, then circuits are a ton of fun. Okay, and if you're going through a maze and you have no other choice in a path, then you've got to keep going that direction. It applies the same in circuits anywhere we have connections with our wires. So if I drew, again, like what I had here, and all I see is resistor 1 going into resistor 2, do I see any other path that once I went through resistor 1, I could choose to go through for my current besides going through resistor 2? No. So this would mean they are in series, which meant any current coming through resistor 1 is the same current that goes through resistor 2. Had no other place to go. You're assuming current, again, does not just jump magically off of your wires and onto other things, because if it does, then our whole properties are going to a mess. So we like to assume they stay confined in our nice wire systems. Now, if I have something like this. Here's R1. Here's R2. So then here's R3. If I'm current going through R1, do I have any other choice but to go through R2? Yes. When I go through here, look, I have a wire I could go this way, or where could I go? Up through R3, okay? So I've got to keep going in a direction, but if I have some other wire or branching point from it, this is not in series. Okay? In series just meant I had no other choice. So you should be asking yourself, in the little maze where I can only follow wire lines, was there any other choice but to go into the next one? That's what it means to be in series. Elements that are in series, therefore, have the same current. There was no other place for that current to go, so it was stuck going from one to the other. If I do have different paths, though, like we saw here, then the circuit elements can have different currents. So the current through R1 does not have to equal here the current through R2, nor does it have to equal the current through R3. In fact, it probably won't, barring other things being weird about it. Okay. That current through R1, we'll learn later, will equal the sum of what goes through R3 and R2, but it doesn't go through here. With that, we also get to what's the difference between an open circuit and a short circuit. Did you all discuss open circuits or short circuits in physics? Well, maybe, no? Okay, we're going to assume no. So an open circuit is kind of like what it sounds. There is an opening somewhere in your nice little circuit maze path. So although we like to assume there are wires or circuit elements connecting everything, what happens if I have something in the middle where a wire comes here and then suddenly nothing here? Again, in the middle of that we assume is air. And air, we said, is a good resistor or a bad resistor? It's a really good resistor. It is not letting current flow through it. In fact, we assume that air has a resistance of infinity. It is a marvelous resistor, and it is really high in its resistance from it. Okay. So in between there, if I have a resistance of infinity, that's for my open circuit, what happens to my current with what we know as Ohm's law? If R is infinity, what is I? If you hold whatever is the same voltage, assume V is the same. Zero, yeah. Because anything from it, to try to make that, has to be zero from it. So no current can go through it. The other way to think about that is we were talking about current in series being it had a path, an option. This is not a path option. There's an open hole from it. Current can't go through there. It's not a place for current to go. So my current through here is zero in an open circuit. A short circuit is where I just have a wire. Again, we assume wires are really bad resistors, or that means they're really good conductors, so they have a resistance of zero. And that means, in my Ohm's law equation, when my resistance is zero here, and I'm trying to hold it to the same voltage, what is my current? Infinity, yeah, it's the opposite of what we had here. So if one goes down to zero, the other one's trying to get as large as possible to make that number work from it. Okay? So this means if you have a wire anywhere, this gets to be really important. And it is just connecting two things. Technically, infinite current could go through that wire. So if you hook up something in lab, like our 5 volts, which we will use most commonly as our voltage source, and you just connect a wire straight from the positive 5 volt side to ground, what current can go through that wire? Infinite. Infinite is scary. We should be scared of infinite. That's why short circuits cause electrical fires in your house. Things from that, because infinite current means infinite number of charges moving in time. The faster they move, the more they heat up. The more they heat up, the more the risk of fire. Okay? So you do not want to short circuit something like that. In that case, I can have infinite current going through it. This also means that it can cause an issue with how we hook it up with resistors. So although this could have been just my 5 volt voltage source here, and if it's an open circuit, there's no connection between here, so I have no current going through it. But what's my voltage difference from one side to the other here? Even though there's no current, what voltage difference, the way I've drawn it here, do I have from here to here? 5 volts. So I can still have a voltage without current. Now, it's not a voltage drop through a resistor, it's just a voltage difference from my voltage source. So I can have a voltage with 0 current. That's like there's a voltage difference right now between your wall outlet prongs, even without something being attached to them to make a current flowing through the circuit. But here, I had a voltage, and I'm basically trying to make it like there's not a voltage difference here. Right? We said there's no voltage drop across the wire from it, so it's like you're trying to make it 0 volts, and it's conflicting with the 5 volts, and it doesn't know what the heck to do, so it just keeps sending infinite current through it, and that's when we get to a scary situation. Okay, if your Echo 360 is working, go back to our next question, if I can. So it's not going to display my answer choices very well. So I'm going to put this up here for a second, and then I'll scroll down to the answer choices if you want to jot down this circuit. I'm asking what current is going through this resistor, R1, right here. R1 is 100 ohms. This voltage source is 1 volt. Here's ground. Ask yourself what's happening here, and what does that mean for that current? If you want to talk to your neighbor, make sure you agree. Fight it out if you don't. Once you've drawn that circuit, I'm going to scroll down to the answer choices so you can see what your options are. Okay, submit an answer if you can. Survey closing in 3, 2, 1. Okay, good. Most people got this right. I got 17 people who want to say 0.01. The correct answer should be 0 amps. Why? Someone who put 0 amps, explain to me why 0 amps.
Because like the current can't flow through the break.
Yeah, so this is an open circuit. So we said what current went through this? 0. If it's an open circuit, right? It's like you had a resistor of infinity. So if that's 0, did it have any other paths where it could go? That's still 0 coming through here and 0 all the way around. There was nowhere else for the current going through here to go through except there. If that's 0, this is 0 as well. If that current is 0 through this resistor, what is the voltage drop across that resistor? If the current through it is 0. 0. V equals IR, right? So if one of them is 0, if the voltage is 0, then the current 0 through a resistor. If the current 0, then the voltage is also 0. So although I have 1 volt difference here, I don't drop any voltage across this resistor. So what's my voltage difference from this point at my opening to here? So I went like ground. I start like that's 0 volts. I gained 1 volt, so now I'm 1 volt. Did I lose any voltage across this resistor? No. So I'm still at 1 volt. So I'm 1 volt here compared to ground. So what's my voltage drop across that open circuit? 1 volt. Okay? It's the same as it was here because I have no current going through that resistor. It's an open circuit. And I have no voltage drop. This means if you build a circuit in lab and there's no path connecting it back to ground or back to whatever its voltage source, then there's no current going through that resistor. Yes?
Question.
Sure.
Using Ohm's law for the open circuit, when
Yep.
R equals to infinity, how is I equals to 0? Is R equals to infinity and then
Yeah, so it's trying to make, so it's trying to like say that 1 volt equals I times R, and that R is infinity. Mathematically, there's nothing that I can multiply by infinity and get 1, right? I mean, unless it's 1 over infinity, right, is really what I'm trying to get that. 1 over infinity, what's the limit of 1 over infinity? what happens is you keep dividing by a larger and larger number. It gets smaller, it goes to 0. So that's practically what's trying to happen regardless of what that voltage is. Even if you're trying to get 5 volts or 2 volts or whatever. It will always be that if R is infinity, that I has to be going to 0. I'm trying to be 1 over that. Yeah, good question. Okay, let's do one more. I now have this circuit. I have a 10 volt voltage source, I have a 10 ohm resistor, ground's down here, got a wire here, the rest of these are wires. What is the voltage drop across this 10 ohm resistor? Talk to your neighbor, see if you agree. I'll let you draw that circuit for a minute and then I'll scroll down the answer choices. Okay, I'm going to scroll down so you can see your answer choices if you've drawn your circuit. Okay, submit an answer if you can. Survey closing in 3, 2, 1. Okay, oh, I've got a pretty even split here between whether it's 0 volts or 10 volts. So what's going on with this circuit? I'm trying to go from 10 volts here, but then I have a wire here. What is the voltage difference from this point, this dot up here, to down here if it's just a wire? What voltage drop do we say to goes across a wire? 0. So although it's trying to make it 10 volts from here, that wire is making it 0 volts. So this is what? What is this wire doing? Is it an open circuit or a short circuit? Short circuit. So this means this resistor here, if I'm going from it, on one side of the resistor is connected with just a wire to another. So what's the voltage drop across that resistor? What do we say the voltage drop was across that wire? 0. So what's the voltage drop across that resistor? Also 0. Okay. Now, it's really tempting to say, but there's 10 volts here. But it's short-circuited out by this wire. So if you ever connect one side of a resistor with a wire to the other, why does current want to go through a resistor when it can go through a path that has no resistance from it? It will choose this path instead and will not go through here. It's acting like a resistor of 0. When we get to them in parallel, you can compare that and see what that does mathematically, but it's making all the current go through here instead of through there. So its voltage drop is nothing. This is the danger of short-circuiting things through this. Technically, this would have infinite current that could go through that, and I have no way of regulating that current because there's no resistor between that voltage source. Questions or concerns about that? You will need to be able to identify in a circuit if you have a short circuit or an open circuit. But more importantly, when you're building it in lab, you need to make sure you don't have a short circuit or an open circuit for anything you're doing. Okay. So with that, we now get to Kirchhoff's voltage law. Did we cover that in physics? Yes, okay. This is what really relates to the equation that I was asking you about mesh, but we'll get to how it actually applies to what's called mesh analysis next week. But Kirchhoff's voltage law basically says that a loop or a mesh, since I'm going to use that term later, I'm going to call it either one, they're interchangeable, is any closed path. As in, I start at one point, and I go wherever the heck I want to as long as I'm following paths in my circuit, so I can't jump through an open circuit, that's not a connection from it, and I end back at that same point. Okay? Any closed path will have a net change in voltage of 0. Did anybody run the Flying Pig marathon or half marathon last week? No, no runners in here. Okay, my husband ran the marathon for the first time. I don't run either. So, my dog and I watched it. Anyway, if you run a marathon, you start at a starting point and you end typically at that same point. You may have thought you expended an obscene amount of energy, but did your potential energy change at all? No. Like if I start in this room, I can run to Mount Everest and back, but when I come back, I'm at the same point. I have the same potential energy compared to ground. Sad, and very sad, and I don't suggest you point that out to marathon runners right after they run. They're all grumpy about that. But it's the same thing in our circuits. As long as I start at some point, I can go through any crazy path I want. If I am back at the same point, my change in voltage, or my change in potential energy, has got to be zero, because you came back to the same point. Okay? So, if I have the simplest closed path, would look like this. I have a voltage source and a resistor. Start anywhere you want. I'm going to start normally always in my bottom left-hand corner. This is normally where I have ground. This is my ground symbol. What happened here is this point is 5 volts lower than this side. This is the plus. So if I call this 0 volts, like for ground, then this is 5 volts. Do I change voltage anywhere going through this wire? Do I change voltage going through this wire at all? No. So if I'm 5 volts here, I'm still 5 volts here. Do I change voltage going through a resistor? Yes. How do I calculate what that change in voltage is? Delta V equals IR. Wonderful. We've already learned. Okay. IR, good God. So I get a voltage drop, and now what's my voltage on this side? I was at 0 volts. Did I change voltage anywhere going through this wire? No. So my voltage drop across this resistor is what? 5 volts. So if I want to calculate the current through that resistor, all I would have to do is take 5 volts and divide by R1, whatever that is, right? Okay. But what tells me is that if I gained 5 volts here, I had to lose 5 volts here. Because I start at this point, I've got to get back to the same potential energy. So I went uphill here, because that was a voltage source. I'll always be going uphill through that. That's giving energy to the system. But I had to go back downhill to get back. Okay? That's what's happening. If I have this circuit, again, start at 0 volts. I go up 5 volts. Here, don't change any voltage. I'm at 5 volts. 0 volts is here. What is my total voltage change from this side of R1 to this side of R2? So from this dot, I'm going to draw up here to this dot down here. What's my change in voltage? 5 volts. Now, I can lose some part of that 5 volts going through R1. That may be half of your hill or a little part of your hill, and some part of it going through R2. It's kind of like also going to a mall. You have $100. You could spend $50 at store 1, $50 at store 2, and come out with nothing. You could spend $25 at store 1 and $75 at store 2. You got to come out with nothing. I like the ones where you have to spend all the money, like Mall Madness. So it's the same idea here with our resistors from it. I got to spend all that energy. It's just I could go down part of a hill here, and then a longer hill here, however I want to do it. This one might be R1, this one might be R2. They can be the same, they can be different. But what does the sum of the voltage drop over R1 plus the voltage drop over R2 have to equal? 5 volts. Okay? Because basically if I gain 5 volts there, I have to lose it from there from it. How do I write the voltage drop over R1? I can always write that as I times R1. If I have some current going through R1, I. Do I have any other choice for that current but to go through R2 in this circuit? No. So how are R1 and R2 related? They're in series. So in series means they have the same current. I had no other option. So the same I call here is the I through R2. So if I rewrite that, I'm going to write 5, make this equation up here, equals I onto, that I was onto R1 plus R2. All I did was pull out, I was multiplied by both of those factors from it. If I wanted to replace this circuit with what's called an equivalent circuit, a way to simplify it, that instead of 2 resistors, I want to act like it was just 1 resistor from it. So I want to replace this with what I'm going to call the equivalent, that had my same voltage source, but only had 1 resistor, which I'm going to call R equivalent. What would that R equivalent need to be to make sure it acts the same as this circuit? The sum of my 2 resistors, because basically what I'm trying to do is get it to be 5 with the same I onto an R equivalent. So what does R equivalent have to equal? It has to equal R1 plus R2. So how do I combine resistors in series? Add them. I add their values. If I had 4 resistors, how would I combine them that were in series? I would add all 4 of them because the same current that went through one would have to go through the next, through the other. They would all have the same I. You would have IR1 plus IR2 plus IR3 plus IR4. Okay? We will be building that in lab this week. So we will be building a circuit of a single resistor, measuring its voltage drop, which should be 5 volts when it's only that. But if I change that resistor, if its resistance changes, will its current change going through it in this circuit? Yes, because that current is based on 5 over R1. The voltage drop won't change because I've connected it from one point to another, but the current will. Here you'll connect 2 resistors, and you need to calculate what current goes through them. It'll be 5 over R1 plus R2, that's our R equivalent. And then you need to calculate the individual voltage drop over each one. That's that I you just calculated times R1 for the voltage drop over R1. Again, from plus here to here, plus here to here, because I gained voltage this way, I lost voltage across these. And the voltage drop over R2. Those voltage drops should sum up to 5 volts. Those resistors weren't adding energy in the system, they were just using up some portion of that energy. There is a lab handout posted. I suggest you look it over before you come to lab so you're familiar with it. Don't forget to come to lab this week. Oh, I also posted, we have a ton of people in Monday's lab section, not so many in Tuesday or Wednesday. If you are interested in switching, if you're in Mondays to Tuesday or Wednesday, come see me now, and we'll talk about it. Good, how about you? Me. Oh, I got it here for you. How'd your first week go?
Two courses this semester instead of just one. That made it a little bit challenging.
Yeah. Yep.
Sorry, 64?
I have no idea.
What the highest score was?
89 point something.
My arthritis is not a happy camper today.
No, yeah, it's supposed to rain.
Yeah,
Hi.
I can tell.
Okay, I had 2 people who thought they were checking in and I didn't have to tell you. No? Okay, let me check.
Between my allergies and my arthritis, I'm in a real great shape today.
Possibility, my office assistant may have put some in my office. Because I had 2 other students sign that, but otherwise I'll just tell you, print it out and write something and give it to you. If I don't have it.
Yeah.
But let me check. What's your last name?
Kelly. Kelly.
Yep, I didn't have a grade for you from that. So unless, if I find it in my office, I'll email you and let you know. Otherwise, there's the pretest is on Blackboard. Just print it out and write something really strong so I can put a grade for you for next week. Yeah, I don't know. I have 3 people now who don't think. So she either put 3 of them in my office one day or something happened weird today.
Alright, will you just like email me if you find it?
Yeah, I'll email you.